I would like to get back to explain to you this question, finding the Higgs boson the homegrown way. I think the question mark is not the Higgs boson. Yes, we found it, but why did we find it the homegrown way? So I will walk you a little bit through this. And I should mention that, as Richard has pointed out already, one of the really different qualities of our projects is that they're really, really long time. I'm working basically for my whole working career since 1995 at CERN. I'm working on a single project, and I actually came late because they started already in '94. So I think with this type of projects, you're either coming late or you're leaving early, and well, we'll see. Maybe I will manage both. Very important to understand the requirements of this system are there's a lot of people involved, a lot of scientists involved, which are physicists who are experts in physics. I think they're very specialized people who are very focused on their physics work. They come from all over the place. There's a large community. Whatever we are providing to them to do is supposed to help them. I think by their original interest in computing is probably for some of them as big as the interest in pencil making was at the time when physics was still done on paper. So for them, computing is a simple tool, and it's very important that we have our main resource, their brains, working as effectively on the data which we are providing to them to do real science, and that's very important to keep in mind. Another item which I just briefly mentioned because Richard covered it, the way how we are collecting data out of particle collisions are very, very complex electronic detectors nowadays, which are collecting a lot of data. This was all mentioned. But the complexity of these detectors maps into the complexity of the data which we actually have to analyze, which is very important to keep in mind as well. The system which we are using to run all this processing of LHC data is very complex as well. It is actually complex because of the way how we collect our funding, which Richard already has described as well. So important to understand here, there's a lot of sites involved. This is not technically the easiest solution, but it's the only one for us to accumulate the funding which is necessary to have enough CPUs, enough storage to do the processing of LHC data. It comes with technical problems like how do we upgrade so many sites? Any kind of product we are using has to be deployable at all those sites and upgradable. And this slide is just a placeholder to show you our current system is actually performing millions of jobs and hundreds of petabytes of data. So we are happy that we got the system that far. We are a project which is in production, and which expects to stay in production for a very long time. At the moment, we are planning the next upgrade, and as you can see, the infrastructure which is at CERN, the blue part at the low bottom, is only a small fraction. We need all those other sites. We need to keep them involved, and we are following some natural progression, which is basically how much infrastructure can we buy for a constant budget. So now, for the next part, I would like to go a little bit back in time. How did we get there? So I mentioned already event, the measurement of one particle collision for us is a rather complex data structure. And to get some feeling for this, it's basically for every single particle collision, we have a tree of objects. There's thousands of objects, which are of hundreds of classes in today's speak. So different record types or whatever you want to call it. And there's quite some intensive relationship between them, because when we have an analysis object, a particle, we can go back and try to figure out from which measurements was it actually obtained. So in this tree, there's a lot of pointers. Between those trees, there's no correlation. They're individual measurements. They are statistically combined. We can compute them in any kind of sequence. But the internal structure is relatively complex, and we have quite a bit of data. You can see that the history of doing this kind of analysis goes back almost to the paper and pencil time, which you see listed there. But that's not how far I would like to go back. What I would like to go back to is the year 92. And why do I go back to the year 92? This is the period when I was doing my PhD. I was still a happy, good-looking, you can't check it anyway because Facebook wasn't around, student. And I was doing analysis myself at that time. And I happened to go to the first conference which our community has actually on computing. And so what was the situation I found myself in? So all the processing was done in Fortran at that time. Of course, you all know how well Fortran is prepared to do navigation in trees. If not, please go to the Wikipedia page about Fortran. It probably has a full language description. And yes, you can multiply and add indexes to find the column which your data value may be. What people were doing at that time was going through these trees a lot with batch jobs, trying to figure out the information they needed for the analysis. And there was one invention which was actually very important for me, because one guy, after you do this tree navigation all the time, came up with the brilliant idea to just create a table out of those objects which I either need to select my events or which I need to do the processing to fill histograms and look at my results. And this sounds very simple, but it was a very important idea because it sped up the process in sequentially going through the data by a lot. So I was very happy about it. So you would take a couple of attributes and use them for the selection, and you would, if successfully selected, you would put your processing on some other attributes from this table. Now, it was very successful. It was used by more than one person. So guess what happens? You put more attributes in there, one for this guy, one for the other guy. You put even more attributes in there for the whole working group. And then the navigation on this becomes ineffective again. The iteration becomes ineffective again. And therefore, people had a brilliant idea of speeding up again this now not so useful table anymore. And when I went to this conference, there was a presentation about performance improvements for n-tuple queries using column-wise stored data, which was a pretty natural idea at that point because you could see that you're reading a lot of useless data, so people put it in Fortran, of course, in a way which was completely unusable to the rest of the world, I guess, but to the physics community, it was part of the infrastructure, and it was very important. Briefly afterwards, people actually constructed a different system which was doing parallel analysis based on the exact same query on a cluster. I'm not pretending this is Hadoop yet. Clearly it's not. It's not, it was a dedicated system for something much smaller, but a lot of the ideas which are used now in the big data area were actually present in the past and have been run in production. Incidentally, there was also another little presentation there, which was a short demo about a server at CERN and a server at SLAC, who were a strange document exchange system, which was called the World Wide Web. Now, why do I mention it? One of the two things was immediately got a market outside of HAB. It was picked up, or not immediately, but it was quickly seen with a bit of engineering. This has enormous potential. It was picked up, even though invented at CERN, but it was picked up by NCSA. There was a usable browser suddenly, and the rest of the story you know. The other system, this analytics with large, somewhat painful data sets, did not have a market at that time. That came a bit later. I think it has come now. So I'm not saying this to claim we have invented some of the things, but I mean, please understand me correctly. Anyway, all of this was Fortran, and it was rather painful, of course. So when LHC was finally funded, and I joined a project at CERN to look at how we do this properly for LHC. And it was absolutely clear, it cannot be Fortran. Everyone will move to C++. It has to be a modern language. And it shouldn't be homegrown code. It should be something commercial which we can rely on, which is properly engineered, and all the rest of it. So what we did, in fact, was similar to the Astro catalog. We looked at object databases. We also found them actually a good match to the complex object model. But there was something ugly happening. By 95, when we started looking, people were estimating we have complete coverage or taking out the relational market by 2000. Well, as you know, it did not happen. There was no market. Technically, I think there were some problems, but it was kind of okay. But it wasn't feasible for a project which has to keep data for 15 years if there's a niche company providing an even working product. So we had to move along. We moved to object relational for a little while and quickly got the feedback from the users. All these vendor object types which pop up in generated C++ header files are not something we want to use with the community and hard code for the rest. So we had to move on. And the next step was basically to use relational databases for the metadata, the part which is actually updated, and use our own homegrown persistency framework for the rest of the data. And you can see actually an earlier talk about the database side, but that's not interesting today, I think. So what has actually started also in '95, in parallel to us looking at object databases, was a second project in-house to try to do object persistency for C++. The management at that time provided consistency by forbidding one of them, actually the one we are using now. But the people working on the project, of course, went on and did the project anyway, which I think we are quite happy about now. So basically, root is using C++ introspection, actually implementing C++ introspection, parsing header files and so on, in order to discover the schema of those hundreds of different classes and providing automatic data persistency. And it actually has a configurable column store for efficient sparse reading access as well. So if this shows a simple picture of how the processing in a root program would work. You start in your pre-selection to look at some top object. You select which events you're interested in based on, for example, only the red objects. And then you pick some others, for example, the green ones, and do further analysis with the data which you're currently interested in. And then you iterate this over the next and the next and the next tree. So that's the basic process. Now, in order to get efficient data access, what is done in root is actually that the different types of objects are streamed in different areas of the file, so that we can keep all the data of one subdetector, let's say, in one area of the file, and all the data of another subdetector in another file, which is optimizing the reading time when, clearly, if you're not interested in all the data. And they have a container, basically, which is keeping track of the logically still tree-like, but flattened structure on disk. You can push this even further if you're not just taking a single object and keep the data together, but you group all the individual attributes by each other, which is typically done further towards the end of the analysis when you have a few quantities, individual quantities, which you will only use one or the other. And that can be actually tuned while you define your data model. You can have some objects which are stored row-like, because the column-wise access is not optimal for all kinds of access patterns. It only becomes optimal if you're reading like less than 10% of all your data. And if you're reading more, row-wise access is actually more performant. Depends on the system, of course. So there's a lot of features in there which I will not go through. I will just leave you the list there. But it's probably important to mention that through this framework, we have access to all kinds of different backend storage, including S3. There's actually, as a joint project with EPFL in Lausanne, there's an SQL interface on top of the root backend storage, which may be interesting for people outside of HEP. We are not that much in SQL query as a language. And there's an evolution of the parallel processing, which we had in PF before, which allows basically to use a whole cluster to do the execution of a query. I will just briefly flash this quote from some people from MapR who have discovered that actually some other people were working in their area some time ago. And I have probably, do I have one more minute? Should I? Yeah. I think the question which is relevant to us, of course, is obviously at the moment we are kind of happy with what we have. I mean, it's working. It's used by a very large community. The question you could ask is, could or should we change to an off-the-shelf product? I mean, we have a 15-year project, which means it's maybe safe to assume that the system we use in the beginning will not be the one we have at the end. And we have replaced a lot of other components already in the running system. For example, storage systems, we did a large move of 40 petabyte from one storage technology to a different one. But persistency is very special in the sense that it's exposed to the programs of very many people. And if we look at the market right now, on our timescales, on LHC timescales, the big data market, which does definitely exist right now, is kind of rather volatile and new, at least if you have to keep data around for 15 years. Many of the projects pop up and get replaced by better ones. That's very good. We are very happy the market exists, but it's not easy at the moment to figure out what will be available on this long lifetime. So if you have a shorter project, things look very different. And concerning the Hadoop parallel processing part, I would just like to mention that getting a quick answer to a single question as quick as possible is not necessarily the thing we are optimizing for. We have 1,000 users running all in parallel on different data, and our current system is doing quite well with just running them in parallel. Because what we are optimizing for is aggregate throughput of the whole batch of them, not a single one of them. So that may become interesting, but it isn't right now. And I would just like to mention that any kind of transition for us with this amount of users and data is a very painful process, in particular if a language change is involved, which affects all the science users. And therefore, we have to be conservative there and really understand what exactly is the benefit. Sustainability definitely could be one, but at the moment, we are not really looking into this. And then I'll just leave you with this summary because I expired my time already. So.